Your interim is February 7th. Okay, your interim is February 7th. Still working on your interim review. It still hasn't gotten printed out. That should be done by the end of today. That being said, if you do not like where you're at in this class, then your interim is what is going to replace your test grades and your mastery checks with it broken down by AKS. So if you see on the interim, hey, you got a 90, I'm not taking the 90, I'm taking it broken down by standards. Okay, so there's that. If you are missing a test, I'm staying after school on Thursday. So if you need to make something up and you are able to stay after, let's go ahead and knock that out. My goal is to be done with all things graded for unit 1, 2, and 3 by Friday. Okay, so with that being said, on your paper, you're titling this characteristics of quadratic functions. Titling this characteristics of quadratic functions. Okay, and we're going to label these pieces really quick. So I'm going to label them in because I know it's a lot of writing. So right here, we've got the y-intercept. These are x-intercepts. This is the axis of symmetry. This is the maximum. And I want you to write these down, and then we're going to talk about them in just a second, because I know it's a lot of information. Okay. And the max is also called the vertex, or the minimum is also called the vertex. So again, okay, so for domain, it's going to be negative infinity to positive infinity, always for quadratic. Okay. Just a reminder, we learned back in unit 1 that with quadratics, we knew it was a quadratic by the U shape. This is called the parabola, or how some of y'all say it, parabola. Okay. Now, range is our y values. So what's our lowest y value on this guy? Well, it goes down to negative infinity. And then my highest y value goes to 6. My range for this one is -1 to positive infinity. Okay, so just as a reminder, domain is your x values, and that's where it goes left to right. And range is your y values that move from bottom to top. Okay. Now, in behavior is where do the arrows actually end up? So looking at the ends of our graph. Okay. So as x approaches positive infinity, so as we go to the right, what's happening to our y values? Where are they going? They're decreasing to negative infinity. As we move to the left, our y values are also decreasing. Can you take a moment and try the next one? So in behavior, as x is approaching positive infinity, what's happening to our y values? They're increasing. As x is approaching negative infinity, so as we move to the left, what's happening to our y values? They're increasing. Okay. But within behavior, we're looking at the arrows. Where do they end up? Okay. And I wrote this list on the board if you need it. So it's going to stay there for a little while. Okay. Now we've talked about increasing and decreasing. Increasing is where it's going up. It's like that roller coaster thing. So increasing, we're going from negative infinity to 1.5. And then it starts to decrease. We go from 1.5 to positive infinity. Can you take a moment and try the next one? So it's increasing from 2 to positive infinity. And it's decreasing from negative infinity to 2 because it's going down. Okay. With increasing and decreasing, we're looking at our x values and like where it happens. Positive and negative is one that we often forget. Positive and negative is where is it above the x-axis and where is it below the x-axis. So looking at this one, it's positive when it's above the x-axis. So from -1 to 4, it's positive. It's negative when it's below the x-axis. So it's below from -infinity to 4. And from, I'm sorry, the -1, JK. And then from 4 to positive infinity. Can you take a moment and try the next one? So positive on this one, we're from -infinity to 1. And then from 3 to positive infinity. For negative, we're going from 1 to 3 because that's when it's below the x-axis. On your paper, I would probably make like a little cheat sheet for like what each thing is. So like up on the board, you see where it says cheat sheet and it has like kind of like the descriptions of everything. I put in parentheses whether you're dealing with x's or y's. Okay, probably be a good idea to just kind of get in that habit of saying the same thing over and over again to yourself. Like domain, I literally go, all right, what's my left? What's my right? Range, I go bottom to top. Okay, so that'll help you just a little bit. All right. Let's go ahead. Yeah, let's go ahead and do this one. Okay, on your paper, go ahead and draw these 3 stages. I want you to answer the question, how would you draw stage 4? And then how would you draw stage 0? Okay, so you kind of have to figure out what the pattern is. So let's talk about this. All right, so what would stage 4 look like? What would stage 4 look like? Yeah.
This stage 4, like the rule for like the pattern of stage number 4 plus stage 4 would be 17 because it would be 16 plus 1.
Ah, okay. So this would be like, excuse my boxes. I swear I can draw better than this. I say that, but y'all see my handwriting. Okay. So it looks something like that. Yeah, those boxes are real bad. I'm so sorry. Okay, so she's saying take the stage number, square it, and then add 1. So let's see if that works. 1 squared plus 1. Yeah, that's 2 boxes. 2 squared plus 1, that's 5. 3 squared plus 1, that's 10. It works. Okay. Now, stage 0, what would that look like? 1 block. Boom. Everybody see how I got that? Why? So, Morgan, can you explain how you went about that thought process?
So looking at the boxes, I was trying to figure out what they're in the free spot. So what I did is I don't even know how to explain it. Like when I looked at the box stuff like last year on the stage, then I was like, oh, they look like square because I was like 1 times 1 is plus 1, and then I was like 2 times 2 is 4, plus 1, and then 3 times 3 is 9.
She said, hey, I have a square here. Okay. So since we have a square, we know that each side is the same, right? And these sides are corresponding to the stage number. This is 3, and look at the stage number. This is 2, and this is the stage number, right? You kind of have to play around with these. Sometimes this comes easy for some people. Sometimes it's a little tricky for others. So I want to show you a different way to look at this. So same pattern. So same exact thing that you had over your paper. But I want you to write this table down. Go ahead and write this table down. So stage number and then the number of tiles. So on this one, let's fill in the little chart. So we got number of tiles. We had 1 in the first one. How many do we have in the second one? 2. 5 in the next one. 10 in the next one. 17 in the next one. What would be 5? 26, how we get that? Okay, so Morgan already said stage squared plus 1, right? So let's write that out in an equation form. Y equals x squared plus 1. Now, if we graph this, this is what it would look like. So it looks something like this. Okay, very similar to exponential, but this is a quadratic. How do we know it's a quadratic? How do we know that this is a quadratic? We don't want to use the word exponentially because that's a different type of function. What you got?
If we do it on the negative side too, it gets the same numbers.
So if we have something like this would be a parabola, right? But we don't have that. So let's take that off. The other way we can tell that this is a quadratic is because this 2 is in the exponent. So quadratics have that x squared. Up a good point. So I'm going to go ahead and start talking about this while you finish it up. Now, we could have done it this way. We could have said, what's the difference between 2 and 1? Like, what's 2 minus 1? 1. Okay, cool. 5 minus 2 is what? 3. 10 minus 5 is 5. 17 minus 10 is 7. 26 minus 17 is 9. Okay. We see that this is not linear because these numbers would all be the same. But if we subtract these again, what's 3 minus 1? And what's 5 minus 3? And what's 7 minus 5? And 9 minus 7. We see that the second difference is the same. Yeah? So if you're like not so great at the whole pattern thing, this is how you can do it. You can make it into a table and find that second difference and see that, hey, this is a quadratic. Okay? So let's look at one more. I want you to write this on your paper, and I want you to tell me if Karen is right or not. Okay, so what'd you come up with? Yep. Times 2. Okay, so let's check our work. So if we plug in 1, we get 1 squared, which is 1, times 2, which is 2, right? So how should you have adjusted this one? We know it's going to be step squared, right? So if we take the step number, that's 1. 1 squared is 1. How much do we need? 2. So we could plus 2, right? What if we tried that? Hey. So on here, what we said was we know that it's going to be squared. Remember our little table that we made? Okay, so here's our steps. We went from 3 to 8 to 15, right? What's the difference of this first one? What's the difference between here and here? 5. What's the difference between here and here? 7. So the second difference is 2. So 2 is somewhere in our equation. Yeah? Okay. We know that we're going to have a squared. So we said, hey, we're on step 1. That means that we have 1 square. We're in step 2, so we have this square. We have a 2 by 2 square. We're in step 3, we have a 3 by 3 square. How much are we going up by each time? So this one already started with 2. Then we multiply by 2 again, right? Then we multiply by 2 again. Do we see it? So when we write our equation, we say x squared, which represents step, plus 2, because that's how much we started with, times the step number. Yeah. Okay, I know these are tricky. Okay, that's why we're starting to practice them. I want you to take a look at these two and see if you can come up with the equations for them. Okay, See if you can come up with the equations. Do you see? I'm gonna help you just a little bit. Do you see how on this first one there's one square? And then here's that square. Here's the square. So we know we at least have an x squared somewhere in there when we write the equation. Do we see it? Okay, go ahead and take a moment. Try those two. Let's talk about this first one. What's going on here? Go ahead, Morgan. X squared plus 2. Do we see y though? We said x squared plus 2. So we've got this square, we got this square, we got this square, and then we're adding two little guys on the side each time. Cool. Okay, on the next one, we got a square, and then how many do we have on the outside? Okay, so we got x squared plus 4. Does that work? Yeah. So sometimes we can see this visually. Oh man, she had a light bulb moment. Ooh, that was wonderful. Okay, do we need to try one more? Yeah, I think we need one more just because she just had that moment. Okay, I don't want you to try the 1B. I want you to try this one. Try 2B. Try that one. On here, when you do these, you kind of want to like box out the squared part. Like take out the squared because we already see it, right? Now, let's look at the empty boxes. So what's going on each time? Well, we've got x squared, right? And then we have these 2. And then there's 4 on here. And then there's 6 on here. So it's changing each time. Morgan?
X squared plus this step on the third times 2.
So 2x, right? Very close. It's right there. So we got 2, and then we multiplied that by 2, which is the step number. And then we multiplied that by our step number. We got 3. Yeah. Oh, you did write that. Oh my gosh. Look at you. What's this? I'm so sorry. Good job. I apologize. I should have caught that. Okay. Now, go ahead and look at this one. Which pattern shows a quadratic relationship? Which pattern shows a quadratic relationship? Okay, take a moment. Yep. You said B. You said B? Okay, good. Why? Okay. What's up? Yeah, I got you coming. I gotta print them out. Okay. Pattern B also, if we take that one dot and we square it, I'm sorry. If we take 0 squared and we add 1, we get that step 1. If we take 1 squared and we add 1 to it, that's how we get step 1. Same thing on the next one, right? And we always want to look for that square patterning. Okay. All right. So go ahead and take a look at the paper I gave to you. The people who haven't gotten it yet, I got you. It's coming. There we go. Dun, 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 dun. Y'all, I'm so excited that this prints now. Yay! Okay. Let's take a moment. So what do you notice? What do you wonder? What do you notice? What do you wonder? Lord. Okay. On your paper, where does the ball initially start? At 0. Okay. What do we call that, like in like real world terms? On the ground, right? So it starts at 0, 0, but it's on the ground, right? What time does the ball start to fall? 1.5 seconds. What's the maximum height? 36 meters, right? We can see that right here. What's the range of the height? How low does it go? How high does it go? So from 0 to 36. And how long is the ball in the air? 3 seconds. Okay, so what you just did is you put everything into real world terms rather than in mathy terms. Okay, I asked you the exact same things though. For instance, right here where it's at 1.5, this is the axis of symmetry. Yeah. The maximum height, that's the vertex. The range, we've been talking about range, right? How long is the ball in the air? This is talking about the x-intercept. Where does the ball initially start? That's talking about the x-intercept or the y-intercept. Okay, so these are all math words that we use. We just call them different things when we talk about real world. Okay? We okay on that? Not too bad? Okay, so you already have this filled out on your paper, which is great. Okay. Go ahead and take a look at this question. Tracy, Kristen, and Bill. Choose the name of the student that you think correctly describes the graph in context. And one is correct. Bill's correct. Why is Bill correct? This is the y-intercept. Okay. What about Kristen? Why? It's about 10.5, right? It's pretty close. So Kristen actually is correct. Okay, and so is Bill. And what about Tracy? So it took the rocket the same amount of time to reach the highest point as it did to land on the ground. So from the highest point, to reach the highest point, as it did to land on the ground. What do you think? Why not? Okay. So it's like 5.5-ish. Well, I mean, like the halfway point is like right here, right? But I guess it depends on how you read this. So it took the rocket the same amount of time to reach the highest point as it did to land on the ground. So is it talking about the entire thing or is it talking about only halfway? What do you think? So is Tracy correct? Okay, so we're going with Kristen and Bill. Man, y'all dead quiet.